Yeah, I'm going to talk about fast accumulation on streams. But I do want to sort of structure this talk in the same way that I guess I came across this problem where this was the solution. So I am going to give some context for a little bit, talking about where this came up during the cryptocurrency protocol development, and then I'll go into the solution and or sort of the story of the solution, eventually getting to the thing that's good. So context. Okay. Yes, I work on a cryptocurrency protocol called Coda. The only thing that's important for you to know for this talk is that in Coda, rather than having all the nodes in the network do the computation required to process transactions, do the process blocks that contain the transactions, most of the nodes on the network just verify a small cryptographic proof that work was done. Something you can kind of think of it like a certificate. And these proofs are really interesting. We use the one called the zk-SNARK, and this is the acronym: zero knowledge, succinct, non-interactive argument of knowledge. And I could go over this in the detail that I understand, but it will take too long. The important thing to know is that we can turn statements that are written in this way into those proof objects. So if we can take any bit of computation, if we can phrase it as there exists data such that these predicates hold on that data, we can run a bunch of computation and create one of these proof objects. So I want to give you a little example. We can say there exists a PDF file such that the hash of the file is AB3, DF33, etc. Okay. And the prover, the creator of this proof, can run some very expensive computation, and it is very, very expensive. But out pops this 100-byte bit of information. It's like a binary string. We can broadcast that to the world, to whomever is interested, and anyone can verify, without trusting the prover, can verify that this statement is true, and they can do so in milliseconds, in a constant amount of time. And not only can they verify that the statement is true, that there exists a PDF file, but they can verify that the prover knew the PDF file. That's the argument of knowledge bit. So I think that's really cool. And there's actually a bunch of cryptographic primitives that have the power to do this in the modern cryptography world. But what's unique about zk-SNARKs is that the verification procedure of these proofs, and I swear this has to do with the fast accumulation on streams. But okay, you'll see. The verification procedure of these proof objects is itself expressible efficiently as one of these statements. And so what that means is we can do recursive proofs. So we can say something like, there exists a proof of this statement such that that proof verifies. And of course, there's no base case here, so like this is unprovable. But if we stuck a base case in, this sort of thing is provable and lets you take a co-recursive process, such as like the production of blocks on a chain or something, but also any other application you can think of, and compress it down to a constant single thing. And just to give you more intuition about this, how this is even like something that could possibly be possible. Imagine we have like a Polaroid camera, and we take a picture, and then let's say I take a picture of you. I give you the picture, and then you hold it up in front of your face, and then I take another picture of you, and this prints out. I give that to you. You hold that in front of your face. I take another picture of you. You do this over and over again. In a single picture, in a single Polaroid, there's evidence, like you can be convinced that multiple pictures were taken. And that's sort of the same idea with these recursive proofs. So, okay, enough of that. The part that matters is that making these proofs is really slow. It's so computationally expensive. So it's about dealing with the slowness. So it turns out the bottleneck is the processing of transactions in our system. So we can factor that out and just think about that. And I want to show you a picture of this, but I need to introduce some notation, or I'd like to. And I like LaTeX, so whatever. Okay, so ready? Okay, notation, sigma. Sigma is the state of everyone's accounts in the system, okay? So I have 10 tokens, you have 10 tokens, Fred has 3, Jane has 20. The whole world, or whatever your world is, has some amount of tokens, okay. We're going to then index that on some slice of time that we look at the world, so like 0, okay? This is the initial state, in other words. And we can transition from one state to another with a transaction. So for the purposes of this talk and think of a transaction as a witness to a state transition. It's a witness to this, specifically to the state, a transition of the state of all accounts to a new state of all accounts. So for example, if I give you $1, we both started with 10 in state 0. In state 1, I have 9, you have 11. Okay. And then we can take that and express it in our there exists such that statement and create a proof. It is possible to do this with zk-SNARKs, create a proof that specifically there exists a sequence of transactions that takes us from state 0 to state 1, namely the sequence containing that transaction. Okay. And now we can actually look at an interesting picture. Okay. So if you wanted to process transactions serially, this is maybe something you might do. So, okay, on all the way on the left, on your left, there's our base case. It's the proof that there's a sequence of transactions that takes us from state 0 to state 0, which is the empty sequence. As soon as we see a transaction, we can take that, combine it with the first proof, and we get a proof that we can go from 0 to 1. We can take that, combine it with the next transaction, a witness to the transition from state 1 to state 2, and we get back a proof from 0 to 2. And we do this again, we get a proof from 0 to 3, and again a proof from 0 to 4. And if you squint at this, it sort of looks like a fold, like a left fold, a little bit. And I think this audience doesn't really need me to explain what fold does. This is OCaml though, so it's not Haskell. Read that. Okay. But anyway, just so everyone's on the same page, if we fold over the list 1, 2, 3, 4, we start at 0, we use addition, we essentially sum everything together and we get 10. The important thing to look at in the type signature is at the end we're returning a single B. So this B is the value that we're accumulating, and in the end of a fold we get one value out. So if we think about it more carefully, it isn't really a fold, it's more like a scan. So a scan is I guess in the fold family, but it's not quite a fold. Instead of getting one value at the end, we get a list. If you look at the type signature, we get a B list at the end. And the example at the top, we get the intermediate results of the fold. So we get 0 plus 1, 0 plus 1 plus 2, 0 plus 1 plus 2 plus 3, and 0 plus 1 plus 2 plus 3 plus 4. Okay, cool. But if you really think about it, we don't quite have a scan on a list. We actually have, because we don't have a list of transactions. Like transactions are just coming in over time. So we have a stream, and we're getting closer to the talk title. And this is not like I guess in Haskell you call your infinite list a stream, but this is not like an infinite list. It's like an asynchronous stream that values are pushed onto it whenever, and you can't just pull them off whenever you want. They're sort of over time they'll appear. Values will appear. So if we have an alpha stream and we have an initial value and a combined function, we can return a beta stream and essentially implement scan. Okay? And that's what I think this process is really. And that's how I think about it. And now we can really, you can kind of see this. At the bottom we have the A's, the stream of A's, our transactions. In the middle we have the B's. The thing all the way to the left is the initial B, and we get the stream of B's out. Okay, cool. And the problem is that these proofs that we're creating is really slow, so we get low throughput. And we have a problem where we need to accumulate streams, and we want to do it fast. Accumulation, we want to accumulate values using our stream of inputs. Okay, whatever. Fast accumulation on streams, that's what we want. So this talk is talking about the problem. We're done with that. And then I guess maybe we need to talk about it a little bit more. I want to dig into the properties of this problem and think about if there's anything that we can exploit, anything we can take advantage of to get a better solution. And then we can try and come up with a solution, but maybe we should think about how we can analyze if one is better than the other, and then we can iterate and start with something really basic, and maybe once I tell you the properties, you'll think of it immediately, at least I did, and then we can sort of improve on it over time. So, okay, properties, right. The proofs are very slow to construct in our system. What does this mean? They're so slow that we don't even have to care about any sort of administrative extra computation that we have to do. The accumulation part of the computation dominates. And then let's say we know that transactions arrive at a constant rate, or an expected rate of R, and for the purposes of this talk, we'll say it's constant, although this approach works if it's not. And then we can say that there exists a distributed work pool in our system that scales with R. And there's like cool cryptography that makes that work, but it's not important. The important thing is we have as much parallelism as we want. Now, if we think about the recursive composition bit and the statements that we're proving, we can take two proofs of state transitions, so one that goes from 0 to 1 and one that goes from 1 to 2, and create one that goes from 0 to 2. And this is just possible to express in the system that we have. And what's cool about this is, well, it's a binary operation, so we ask the question, is it associative? And here's a nice visual proof of that. So it's kind of like the wiring diagrams that David Spivak talked about in the beginning, I guess, if you turn it sideways. But on the green side, we have 0, 1, and 1 and 2, and we do that first to make 0 and 2. And we can take that and combine it with 2 and 3, and we get 0 and 3. And on the red side, we have 1 and 2 and 2 and 3 that we sort of group together and combine 0 and 1 with 1 and 3, and we get 0 and 3 again at the end. So this operation is associative, and associativity implies that there's parallelism that we can use. But just to summarize, if we have this expensive accumulation function, we have the fact that our input arrives asynchronously over time, and we'll just say it's constant for the purposes of the short time that I have in this talk. We'll say that we have plenty of parallel compute available, and we have an associative merge operation. And that's what I have. But if you read this list and you have something that fits in that, has these set of properties, and maybe this sort of solution you can use for something. So when we're thinking about our solutions, we should, when we're sort of judging them against one another, we should first try and prioritize maximizing the throughput that we can accumulate our data in, if that makes sense. So we want to process transactions as quickly as possible. That's the point. That was the original problem. But once we do that, the next most important thing is to minimize latency. If we have a piece of data that we're going to begin work on, once we receive it, it should exit as quickly as possible out of our scan. And then after that, the next most important thing is to minimize the size of intermediate state. And this is because we have this distributed work pool over the network, and we have to send bytes around. And so the fewer bytes we have, the better. OK. And now we can throw away the details of the problem now that we're halfway through the talk. But so let's just say A is our data. Just like in the type signature, I'm going to index it with the 0 at the bottom, 1 at the top to sort of show you the transition. And then B is our proofs. So just like in the earlier type signatures as well. And I'll show you how this fits into the sort of tree structure that we're going to be building in a minute. And so let's do that. Let's do something faster. So the first thing, I call this the naive solution, because as soon as you know that there's parallelism in an associative operation, this is sort of the first thing that one would think of, I think. So first of all, in this example, R is 8. So in every step, we're going to have 8 pieces of data available to sort of do something with. So in this case, I'm taking the 8 pieces of data and just laying them out, okay? And then in the next step, in the next unit of time, we're measuring time by enough time for the computation to be done. we can do it in parallel because we have our work pool, everything gets done. And then in the next step, there's half as much work to do because we can merge things together. And the next step, we can merge things together. And the next step, we can merge things together. And we're left with something that we can sort of emit and return from our scan. And okay, the first thing that you should think about here is that, well, this isn't really a scan because we're not returning all the intermediate results. So this is kind of like a periodic scan, if I were to make up a term. So what? Okay, this is kind of like a scan, but let's look at the type signature first. So we have a stream of data, and then we have an associative merge operation that acts on B's, but we get A's in, so we have to have a function that can take us from A to B. And we have an initial state B again, and then we're going to return the B stream. So it's basically it's similar to this folding operation. And then in the example here, let's say our period is 4. That's sort of an implicit thing when you're implementing this, I guess. This is like an ideal type signature. This isn't actually what it looks like in the code, but just to give you an idea of what's going on. Here, we're still doing this scan-like returning of intermediate results, but we're not doing so at every step. We're doing so at every 4 steps. So we're saying 0 plus 1 plus 2 plus 3 plus 4 to get 10. Then we're doing 10 plus 5 plus 6 plus 7 plus 8 to get 36. Okay, so, right. And then if we look at this more closely, what's nice about this, if we think about throughput with respect to the serial solution, in every step, we were only returning one piece of information to our scan. We're only emitting one B, even though, and we were getting one piece of data at a time as well. So, but here, in log R steps, in this case, like, well, O of log R steps, we're returning a value that corresponds to R pieces of data at the end. So you can kind of say that in the serial case, it took R steps to emit something that corresponds to the R pieces of input, and here it takes log R steps to emit something that corresponds to that corresponds to R pieces of input. So it's faster. There's some latency though, because we start at the bottom of the tree and we work our way up, one step at a time, whereas before there was no latency. But otherwise it's pretty good. So yeah, throughput increased, latency increased, and the state size, we have to keep a tree around instead of a single value. Okay, so there's a problem with this approach though, and this is something that was not obvious to me and my team when we were thinking about this, or rather the solution was not obvious, but the problem is kind of in your face. We have a work pool that scales with how quickly the data is coming in. So, and data is always coming in. So why are we having our parallelism at every step? Like when we have a normal tree, we have half as many things to do as we work our way up. So anyway, let's not do that. So let's do this again. This is a different approach. We're going to set R to be 4 because there's going to be a lot more intermediate data here, and so it needs to fit on the slide. But this works for any power of 2. So okay, the idea here is let's always use the data at every step that we get. And we're still going to make trees, but we'll just make more trees. Okay? So step 1, lay out the 4 pieces of data. Okay. In the next step, we can compute our first base proofs, our first bit of work on that data, and lay out the next 4 pieces of data. So in a sense, we're starting a new tree as we're working on the first one. And in the next step, now instead of just having 2 pieces of work to do, and like if we were making a single tree, we have the 2 pieces of work on the first tree and 4 on the second tree, and then we can enqueue the next 4 pieces of data. And now we have 1 on the first tree, 2 on the next tree, and 4 on the last tree, and we can enqueue 4 more pieces of data. And at this point, we can return one value to our periodic scan. We can sort of we've completed the first bit of work, In other words, our latency is still logarithmic with respect to the input rate, because we worked our way to the top of the tree. But what's interesting is now at every single step, we complete another tree. So here's another step. I'm just shifting everything over. Now that our pipeline's full, this pattern repeats forever. And if you don't actually have data coming in at a constant rate, as long as you're careful about the order in which you do this work, everything still works out. But what this means that at every step we're completing one of these trees and we're returning a value to our scan caller, in a sense, it means that our throughput is R. So the input throughput is R. We're getting R pieces of data at every step, and we're emitting an accumulated result that corresponds to that R pieces of data at every step. So our throughput is perfect. We're able to compute on the data as fast as it comes in. And our latency is still logarithmic. It's just that our state size is a bit bigger because we have to keep more trees around. So this is great. But we can do better. We can think about space more carefully. So everything in red is sort of a waste of space here. Because once we do a bit of computation, we don't need that information anymore. We don't need to store it anymore. It's done with. We have our accumulated value that already handles all of that bit under the tree. And we certainly don't need the bits in layers of the tree above us, because we haven't gotten there yet. So what you'll notice here is it turns out we had log R many trees that we were keeping track of. And so and we only used one layer from each tree. So what we can do is just overlay the trees on top of each other. And I colored them in like so. So I think of this as if there's still like the frontiers of these log many trees, but they're just collapsed into one tree. And now when we take a step, data just flows up. So the cyan goes to the B layer, and the red goes to the next layer, and the purple goes to the top, and we include new data at the end. So this is better. We're now doing this in just log R amount of space in the big O sense, and the throughput's the same and the latency is the same. So we're getting better. But now we can start thinking about data like not in the big O sense, but in the sort of bytes sense. We can just change the way we think about data so that it fits in a perfect binary tree, a complete binary tree, and then we can use the trick, the implicit heap trick that you may have learned about in data structures class, where you can just represent all the data in your tree in one flat buffer, and from any point in this array, just from the index, you can compute where your children are or where your parent is, just by dividing by 2 or multiplying by 2 and optionally adding 1. And there's a whole family of succinct data structures that it's really interesting to read about, but we don't have time to talk about. The actual implementation of this in our project is succinct and not implicit, but this presentation of the data structure is implicit. Okay, so and that's basically what we did, and this worked really well for us. But I think this can work in other places. So, for example, there are these huge radio telescopes in Australia that they get like terabytes of data per minute and per second. Sorry. And there's like non-parametric machine learning workloads. I don't really know much about machine learning, but I'm told that it's associative. And anyway, this approach scales with R, so you just have to get a big enough compute cluster. And I don't have time to go over the other thing, but whatever. The point is, if you have any sort of online MapReduce type workload, then this approach, I think, will work for you, assuming you have a big enough cluster. What's interesting to me is that if I type in online MapReduce into Google Scholar, there's nothing that comes up that talks about this sort of approach, but it seems like something that someone probably has done before. So if you know about this, talk to me afterwards. Because I would really like to know where the prior art is. Right, so what do we do? We talked about the problem, so you had some context, and then we dug into it and we figured out which parts of it we could poke at to get the to figure out exactly what we needed to care about when we thought about solutions. We talked about what we would care about when we're judging solutions against one another, and then we iterated. We started from the simple thing, given that there's parallelism, and we worked our way up to something that has perfect throughput, acceptable latency, and space that is only a little bit more than the entropy of the information that we're storing. And that is it. And that's me, the slide deck, Coda, and succinct data structures.